give you a random example, like if I give you like a bunch of problems in a row, then naturally kids will say, which one do I use? So how do I know which one I'm going to use? How do I know to use the central limit theorem on these guys? What tells me that? Sample. I have a sample. Sample is what variable? N. I got to use it somewhere. So whenever I see the sample, then I know I'm looking at that. If it's just strictly a population and I'm pulling one random person, don't forget all your sampling is always done randomly, so don't look for the word random. Look for how many are in your sample. That's your N. So that tells me I have to change my standard deviation. And again, instead of doing both graphs, because then it would be too difficult to relabel your x-axis, just do the one with your sample, because that's the one we kind of need to see. And you'll see how close they are.
What is your percent error for your success? Because I plugged in upper, lower, and then they just came out like
close, right?
Very close.
Yeah. Well, how far off?
Yeah, 94.07.
You're fine.
Okay.
You're fine. Don't forget, look what happens here. I knew that was going to happen to me. We round in a couple of places. We round here. We rounded here. We took the areas from the table because we rounded, and then we subtracted them. Your calculator is all exact. Everything is exact with your calculator. So you're absolutely fine with the calculator. And when you do the calculator, just tell me calc, tell me what you put in, and if it's a test, of course, I'll work it out. I usually just do the formulas on the homework just because, I mean, if I have half the kids that do the formulas, I need to show them the formula. So I just usually do the formula on these guys. Okay with this? You tell me if there's any questions. And then in between, don't forget to set your thing up. Technically, it should look like this, X bar, because we're actually looking for the mean. The mean is your average of all the sample ones you did. The mean of the means. The hat size. Okay, did you locate both of these?
Yeah, I also see areas before I can calculate the calculator in
9407? Oh, you're just a little bit off. So did you do yours in the calculator? Yeah, that's fine. Yes. The calculator is just a little bit more exact, actually. So that's absolutely fine. So then you would say calculator, and I would have done it out with the calculator. The homeworks, I just do it out with the formulas. I don't bother with the calc, because then, you know, if you did the formula, if you did the calc, you'll be within the ballpark. Now, I don't know what happened here. This got all messed up. Let's see what happens here. Oh, that's not right. Oh, that's not right. I don't know what went on here. Something went on with this page jump here. Can you all make this out okay? It's got a probability statement in here. Probability that it's greater than 66. Some of them that I fixed after that we switched to the new one got a little bit messed up. I don't know what was going on up there. So here's a good one. That must be my graph up there. When you're doing this, and you've got a z-score. Here's my graph. Here's my z-score that we can go up to. This is what your table goes up to. Just because we got a z-score of 4.81, it's up here somewhere. Virtually, what is the area to the left? 100%, virtually, approximately. What is the area to the right? 0, approximately. So when you're off the table on the right side, the area to the left is approximately 100%. The area to the right of it is approximately 0. If I'm off the table on the left-hand side, The area to the left is approximately 0. The area to the right is approximately 100%. Yeah.
Do you have to subtract your z-score from 1?
Nope, never subtract your z-score from 1. You would subtract your area from 1. So if the area is 100% or 1, and we subtract 1 minus 1, that gives us our 0. Because we want anything to the right, but never subtract your z-score, just your areas. Now, sometimes it's hard to see because how do I look this up on my table? I can't look it up on my table. So I have to know that anything to the left of this is 100% or 1. Area under my curve is 1. So if I want it to the right, well, it's virtually 0. Okay? I know that tends to get a little bit confusing. All right? 33. Go back to example 31. Assume your heights are normally distributed again. Are you more likely to select, and this, I like these problems, one woman with a height less than 70 inches. This is your population. It didn't say from a sample. It said a random person from your population. So when you do this, you use the regular standard deviation. This is like example 6 that we did in your book. Or, you got to do this again, are you more likely to select from a sample of 20 women, a sample that has a mean height? You're pulling out your sample, so this sample has a mean height of less than 70. So we want to know which one you're more likely to get, okay? Now, the one with the better percentage is the one you go with, right? Makes sense. They're going to be close, but this guy, which is your standard deviation, wasn't that large. So, and your sample size was what? 20. Now, again, not too large. So we did this one. We found what your z-score was. We looked at the area to the left. Then we did this. We changed this. That's all we changed. Divided by the square root of n. And we kind of come off of our curve right now. Our z-score is off of our curve. But the area to the left is, God bless you, is approximately 100%. So which one are you more likely to go with? The one that was 100%. I get it that they're close, but the 100% is better. You're more likely to select a sample of 20 women with a mean height less than 70, rather than one random person from your population with a height less than 70. So see how this makes sense? Pulling one person versus a sample with an average there. Okay. You can tell from your z-scores. This z-score is off your table. It's out of the range of your z-scores. So anything to the left is 100%. It has a higher z-score. To the left, higher z-score, larger probability, right? Everybody can do this one. This is an important one. Okay. Number 36. Now, sometimes they ask them this way. We saw this before. Does this machine need to be reset? So, if it's unusual, then we're going to reset it. If it's very unusual, we're definitely going to reset it. But we're kind of just judged by the unusual. And again, if it's less than 5%, we consider it unusual. So a milk is set to with a mean of 64 and a standard deviation of 0.11 ounces. You randomly select 40 containers and you average them all together. You find what their mean is. And you want to know, does this need to be reset? That's not the mean of your sample. The mean of your sample is still 64. This is still the mean of your sample. This is just the x value that you're going to use. Is this off my chart? Is it an unusual value? And don't forget to use your new standard deviation. You made it even smaller. You made that less variance. They're closer to the mean. So you find your z-score is almost to 3, which is very unusual. So yep, we are going to reset this machine. Plus or minus 2. We say unusual. Plus or minus 3, we say very unusual. So if it's something is black, then yeah, you're going to reset it. Either you're giving them too much or you're giving them not enough. And they have all guidelines, consumer guidelines that judge all those things. So you have to stay within your guidelines. Okay, and 37. 37, you have lengths of a lumber that are cut. They're normally distributed. They tell us normally distributed. Then we know from a population of normally distributed, our sample will also be normally distributed. So you're randomly selecting one board from your population. Is there any N in here? Did they say any sample size? Then you know your population. So you're randomly selecting one from your population. Then you're looking at it greater than 96, so this is where you subtract it from 1. You subtract the area from 1. Then you're looking at a sample. A sample of 40 boards. There's your N. So we want to keep the same thing, but now it's just the sample means. You changed your standard deviation. You made it a lot smaller, and then you're going to compare that. So notice how much closer they got. I don't know where this one either. Way down here. So we can see that my z-score is now very close to the end. So to the right, it's very small. So when you compare your probabilities, the sample is unusual. So the other one is about 31% of the population. You're going to go with the other. Be careful which side you're on, the right or the left.